The cosmos. When we say this word, we usually imagine a dark abyss, freezing and lethally dangerous. There are myriads of stars scattered across its endless expanses, from barely visible red dwarfs to blue giants that sear away anything within their reach. And this image is absolutely true to life. But it is also true that the universe is full of amazing and wonderful worlds. They're so numerous that it is next to impossible to estimate their number. Excitingly, every planet out there is unique in its own way, which means that their diversity is simply incredible. And even though humans cannot go beyond our native system at this point, we can still make a virtual journey around the most remarkable of the worlds already known today. We will start off near the TESS Orbital Observatory, which enabled us to take a slightly deeper peek into the fascinating abyss of the cosmos. With its help, we will visit the environs of the dim red dwarf TOI 700 to make acquaintance of its wonderful planets potentially fit for life. After that, we will go to the Teegarden star to observe the most Earth-like planet of all those discovered by now. Next in line is the bizarre world of Gliese 1214b, which falls into the exceptionally rare category of ocean planets. Then we will reach two representatives of the most furtive and mysterious celestial objects, rogue planets. Deprived of a parent star's warmth, they roam the depths of space for billions of years, avoiding anyone's curious glance. After these dark and cold worlds, we will see a selection of various space objects which have one thing in common: their incredibly lethal properties, extreme temperatures, harmful radiation and a harsh environment. With all these combined, these planets are truly horrifying. Let's get ready, and we begin. Kosmo. The first exoplanets were discovered back in the late 1980s. Since then, the number of detected ones has increased hundredfold. According to statistics from January 2021, over 4,000 planets in other systems have already been discovered. Apart from these, several thousand candidates likely to be given this status have been registered. With sufficient evidence from Earth-based observatories, most of them are going to become officially confirmed exoplanets. The overall number of planets in our galaxy may supposedly be over 1 trillion. From 5 to 20% of these are close to our Earth in terms of their size and composition. Not all of them are in their host star's Goldilocks zones, that is, not all of them are habitable. Still, according to scientific estimates, there are not less than 300 million potentially habitable planets in the Milky Way. Exoplanets differ very much in terms of their environment. Their dimensions may be enormous, some even beating Jupiter, but there are also comparatively smaller ones, close to our Earth in size. Some of these bodies are hot, consumed with oceans of molten lava, whereas others are encased in a shell of permanent ice. There are planets out there made entirely of oceans, with not a bit of dry land on them, while on others, sulfuric acid rains or diamond snow are a regular occurrence. Various techniques are used for discovering other worlds. As a rule, it is next to impossible to spot an exoplanet by simply looking through a telescope. That is why in 2009, Kepler was launched, the first space telescope designed for searching for planets beyond the boundaries of the solar system. The telescope's cameras had 42 charge-coupled devices, or CCDs, with a total resolution of around 96 megapixels. With a field of view covering about 25% of the sky and coupled with a 1.5-meter mirror of the telescope, it was able to detect astronomical bodies within 3,000 light-years from the Earth. In the 3.5 years of productive operations, Kepler managed to spot over 3,500 exoplanet candidates. The status of over 2,000 of these has already been confirmed by repeated observations. It was in this period that the smallest of known exoplanets today was detected. The diameter of Kepler 37b is just 35.7% that of the Earth. The telescope was also instrumental in registering several stars and brown dwarfs. The transit method was used by Kepler in the search for exoplanets. This method is based on observing the star's luminosity. If the supposed planet passes between the parent star and the observer, this will be noticed in the telltale decrease in the star's luminosity. The extent of these fluctuations in luminosity directly depends on the ratio of the stars' and planets' dimensions, while their regularity allows one to estimate the object's orbital period. The transit method requires accuracy in measurements. Changes in a star's spectrum account for less than 2% and are usually tenths or even hundredths of 1%. Ripples in the atmosphere, dust and precipitations negatively affect results produced by Earth-based telescopes. That is the reason why telescopes based on automatic space stations are used for searching for objects beyond the boundaries of the solar system. Unfortunately, in 2013, 3.5 years into the mission, the Kepler Space Telescope had several major equipment failures. In 2018, the spacecraft ended science operations completely. Kepler was the first spacecraft to be created specifically for looking for exoplanets. However, most of the objects it managed to spot happened to be too remote and dim to study them in any satisfying detail. That is why the next space research complex had slightly different parameters. Kepler was succeeded by the TESS telescope launched by NASA on the 18th of April 2018. Its main object was searching for rocky exoplanets orbiting the brightest stars within 200 light-years from the Sun. This telescope also used the transit method. And here is the spacecraft's brief profile. TESS is equipped with 4 refractors with a 24 by 24 degree field of view and a 10 cm aperture. The spacecraft's peculiar orbit allows it to cover both the northern and the southern parts of the sky, which is approximately 85% of the entire sky. Photos are taken by 4 cameras, and the resolution of each camera's CCD is 16.8 megapixels. TOI 700D is one of the most notable objects discovered by TESS. This exoplanet became the first object of the kind comparable to the Earth in size and which found itself in the habitable zone of its star. It orbits TOI 700, a red dwarf lying slightly over 100 light-years away from the Sun. It is a small and rather cold star. Its temperature is half that of the Sun, and its mass and radius are just 40% those of the Sun. TOI 700 is peculiar for its high stability. Not a single flare has been registered on it since the beginning of observations. A star's stability is a positive feature, because bursts of activity are able to divest its planets of their atmospheres and be generally pernicious for potential life on planets' surfaces. There are at least 3 planets orbiting TOI 700. The one closest to it, TOI 700b, is comparable to the Earth in size. Its mass is approximately 1.07 times that of our planet, and its radius differs from that of the Earth by not more than 2%. Unfortunately, TOI 700b is too close to its host star. It is within about 0.06 astronomical units, and a year on the planet lasts just 10 days. In addition to that, chances are it is tidally locked, that is, it faces the star with one and the same side. This means that the planet is likely to be scorching hot. The planet lying further from its star, TOI 700c, is thought to be a mini-Neptune. Its mass may be from 5 to 13 times that of our Earth, and its radius is 2 or 3 times that of the Earth. It takes TOI 700c 16 days to complete one orbit around its host star. Located closer to the star than the inner border of the habitable zone, it must be too hot for life to originate and evolve there. TOI 700d is the third and at this point the remotest planet in the system discovered by now. It takes 37.4 days to complete a full orbit, which by the way lies along the inner edge of the habitable zone. The mass of TOI 700d hasn't been gauged precisely and may be anything from 1 to 3 times that of the Earth. At the same time, the planet's radius is just 20 to 30% bigger than that of the Earth. TOI 700d is thought to be a rocky world, but its exact composition is not yet known. The amount of energy received by the planet from its star is 86% that of the amount we receive from the Sun. Assuming the planet's atmosphere is similar to ours, the steady-state temperature on the surface of TOI 700d is estimated at 268.8 Kelvin, or 4.3 degrees Celsius below zero. However, due to the greenhouse effect, or other features of the atmosphere we may not know yet, this figure may shift either up or down. There is no precise data on the eccentricity of TOI 700d, but it is thought to be small at around 0.11. As the planet's orbit finds itself at the inner edge of the Goldilocks zone, the planet's eccentricity, however small, may incidentally turn out to be perceptible when the planet comes too close to its star from time to time, thus actually leaving the habitable zone. Still, with a year on the planet lasting slightly over 1 Earth month, such unfavorable periods are expected to be rather short. If there are living creatures on TOI 700d, then they might be able to weather the harsh spells in a state of anabiosis. Alternatively, they could adapt or migrate to less inclement areas. Even though the data acquired by spectral analysis of TOI 700d can't be enough for making conclusions, there is a chance that there is liquid water on the planet's surface. Then there is bound to be the greenhouse effect too, which will help the surface temperature to reach favorable values. As I've already mentioned, TOI 700d, along with the other known planets in the system, is highly likely to be tidally locked to its star. If this is the case, there should be a stark difference in temperatures between the sunny side and the shadow side. This contrast could be leveled off by a dense atmosphere, but that would cause powerful hurricane winds. Although the main mission of TESS has been accomplished by now, it still has enough resources to carry on operations. The telescope will continue taking snapshots of the sky, including the Milky Way plane, which is the most challenging direction for observation. Over 2,100 exoplanet candidates have been discovered by TESS in the course of the main mission. Not less than 66 of them have already been confirmed. Apart from that, 6 supernovae flares have been registered, 3 exocomets identified, and a great number of photos taken of small bodies in the solar system. The latter were not objects of the main mission, but are of course of scientific interest. Before we set out on a space journey beyond the boundaries of our system, we have to decide on the manner of selecting a planet that resembles the Earth most from thousands of candidates. What should be the parameters of this fascinating world, and what should we take into consideration first? It goes without saying that planets favorable for the genesis and sustenance of life have always posed considerable interest to scientists. However, it is no easy matter to single out suitable celestial bodies among a great number of those discovered by now. To have clear-cut selection criteria, scientists worked out the so-called Earth Similarity Index, or ESI for short. It is based on several principal parameters: a planet's radius, density, and average surface temperature. This combination makes it possible to calculate the object's mass, approximately estimate its chemical composition, gravitational level, whether or not there is an atmosphere, and if there is, analyze some of its characteristics. It also helps establish if there is liquid water on the planet's surface and other information. The standard of this index is the Earth, with its parameters assumed as ideal and its ESI equaling 1. Based on the Earth Similarity Index, all the objects known to us conventionally fall into 3 categories. The first one is objects whose ESI is under 0.5. These are for the most part gas and ice giants. as well as extremely hot or, on the contrary, cold objects. This is the category most of the solar system planets and satellites fall into. It takes just one characteristic to greatly exceed the maximum permissible values for a celestial object to be unfavorable for the genesis and sustenance of life. Let's take Venus, for instance. The radius and mass of this celestial body are very close to those of the Earth. However, due to its close proximity to the Sun and a dense atmosphere, its surface temperature is extremely high. That is why, in spite of a close similarity to the Earth on the face of it, Venus's ESI is not high, at just 0.44. Of course, there being any life on its surface is totally out of the question. Celestial objects whose ESI is within 0.5 to 0.7 fall into the second category. These objects resemble our home planet noticeably more. They're mostly rocky worlds with relatively moderate temperatures, but it can also be ocean planets and even some large satellites. Incidentally, a high Earth similarity index per se does not warrant favorable conditions for life. For example, quite often low-mass planets are incapable of retaining a dense enough atmosphere, while their magnetic field is too weak to protect the surface from lethally dangerous radiation. Other celestial bodies yet may happen to be located too close to their parent star and so get tidally locked. Of course, all these factors greatly reduce the chances of life's genesis and sustenance. As for the third category, it contains celestial bodies with a high ESI, that is over 0.7. All of these planets are beyond the solar system. According to estimates, the size of these worlds and the conditions on their surfaces are potentially close to those of the Earth. Among these planets, there is one which resembles ours most, and it lies just 12.5 light-years away from the Earth. This amazing world orbits Teegarden star, a small red dwarf discovered in 2003. This star is 1,370 times dimmer than the Sun. This means that it cannot be observed with the naked eye, even though it lies quite close to the Earth. The mass of this tiny star is roughly 9% that of the Sun, and its radius is about 5% bigger than that of Jupiter. Gravitational forces are barely strong enough to maintain the thermonuclear reaction in the star's interior. That is why the surface temperature is just 2,900 Kelvin, or roughly 2,630 degrees Celsius. As is the case for all red dwarfs, Teegarden star's habitable zone is comparatively narrow and located very close to it. Back in 2019, 2 exoplanets were detected in its system after continuous observations of the star's proper motion. Interestingly, one of them lies beyond the star's habitable zone and the other within. The outer planet, dubbed Teegarden C, follows an almost ideal circular orbit around the system's center. With the orbit's radius 0.045 astronomical units, it is completed every 11.5 days. It is presumably a rocky celestial body with a mass 11% bigger than that of the Earth. Its radius is estimated to be approximately 3.5% bigger than that of our planet. Unfortunately, conditions on Teegarden C's surface are far from hospitable. Due to the low luminosity of its parent star, the object enjoys 63% less energy than what the Earth receives from the Sun. As a result, the planet's surface temperature is gauged at 47 degrees Celsius below zero on average, which is too low for life sustenance, at least in the forms we know it. Still, the chance of there being vast oceans of salty water concealed under a thick layer of ice on Teegarden C, as is the case with Jupiter's satellites for instance, shouldn't be ruled out. As for the inner planet, it is dubbed Teegarden B. It is actually this planet that is the most Earth-like object of all those discovered to date. Its ESI is 0.95, which is just 0.05 less than the standard ideal value of our Earth. This celestial body lies 0.025 astronomical units away from its star, and it takes it roughly 5 days to complete a full orbit around it. By following a practically circular orbit, the exoplanet is constantly in its star's habitable zone and it receives 15% more radiation from it than the Earth from the Sun. According to some estimates, Teegarden B's mass is just 5% more than that of our planet. As for its radius, it differs from that of the Earth by a minuscule ratio, which means that the gravitation value is also quite close to what we're used to on our home planet. This makes it logical to assume that the inner makeup of the exoplanet is highly likely to be similar to that of the Earth. There is a massive metallic core coated in a thick layer of molten silicate mantle reckoned to be at the center of the planet. The celestial object's outer part is covered with a relatively thin crust of solidified rocks. Mathematical modeling shows that the average temperature of Teegarden B is 28 degrees Celsius, which is 14 degrees more than that of the Earth. This means that conditions on its surface allow the planet to have and retain an ocean of liquid water, and the planet's temperature profile is potentially favorable for most microorganisms. Even though Teegarden B is quite massive and is capable of retaining a comparatively dense atmosphere, the radial velocities method, which is used for exoplanets detection, is quite inadequate for obtaining any information about the atmosphere's composition. But it should be borne in mind that a planet's temperature profile directly depends on its atmosphere's composition. For example, a dense atmosphere with a high percentage of methane and carbon dioxide will cause a strong greenhouse effect. Dense clouds of water vapor, meanwhile, will on the contrary reflect sun rays, which reduces temperatures. We should also remember that no matter how optimistic the parameters of this fascinating celestial body might appear, it is not entirely flawless. Being in close proximity to its parent star, it seems that Teegarden B is always facing it with one and the same side, which causes sharp temperature differences between the day side and the shadow side. As I've already mentioned, Teegarden's star is a red dwarf, and this class demonstrates a tendency to suddenly flare up. The amplitude of fluctuations in its luminosity may reach 30%, which greatly affects the planets located close by. Still, the chances of Teegarden B's capability of sustaining life are high. Biological creatures often demonstrate incredible viability, and their ability to adapt can't but amaze. For example, the ocean could serve as protection against lethal radiation and sharp temperature fluctuations. Its upper layer is potentially capable of absorbing cosmic radiation, while its currents could dissipate temperature contrasts. For all we know, as time goes by, primitive organisms might evolve in the warm depths saturated with energy and microelements. Just a tiny chance is sometimes enough for life to develop into something bigger. The first steps in theoretical confirmation of there being ocean worlds out there, that is, planets fully covered in water, were made back in the 1970s. That is when evidence was found that radioactive decay in a planet's interior and tidal forces may cause water ice to melt and subsequently form huge oceans. In all likelihood, similar processes take place on Jupiter's and Saturn's satellites. However, these celestial bodies remain icebound as they lie too far away from the Sun, whose rays would otherwise melt the thick layers of ice. But when we talk about an ocean planet, a slightly different type of space object is meant. The term implies that the ocean on a planet's surface isn't concealed under a layer of ice, and its depth measures more than 100 kilometers. Theoretical calculations of these planets' formation and evolution processes were carried out in 2004 by French astrophysicists headed by Christophe Satin. According to this theory, if the mass of a forming planet is more than 10 times that of the Earth, this starts to actively attract hydrogen and helium from the gas and dust cloud around it. In this manner, with time, it grows into a gas giant. By contrast, if this planet's mass is just 6 to 8 Earth masses, the new planet is going to be comprised of ice and rocks roughly in equal measure. Just to compare, the mass total of all water in the global ocean on our Earth accounts for just 0.025% of the Earth's total mass. In this case, Provided a space object's orbit lies far from the host star, this object is going to be either an ice giant or a cold super-Earth. Radioactive decay taking place inside the core will help melt some portion of the ice, which in its turn will help form a subsurface ocean, but the planet's outer layers will still remain frozen. If the planet happens to find itself in its star's habitable zone, its outer layers will melt and spill all over the surface in a boundless ocean. Theoretical calculations show that a planet with a mass 6 to 8 times that of the Earth may have a layer of water over 100 kilometers thick. The pressure exerted by this amount of water may reach 20,000 atmospheres, depending on temperature, impurities and other parameters. This is enough for some special exotic varieties of ice to form, like ones remaining solid even at high temperatures. In addition, unlike the familiar water ice, these modifications would be heavier than liquid water. For example, the density of ice 7, which is likely to form in these conditions, should be around 1,650 kilos per cubic meter. This ice settles on the planet's ocean's bottom and forms a massive cryosphere that envelops the more massive core. The opportunity to put these theoretical assumptions to test arose when a tiny and dim star was spotted 42 light-years away from the Earth. It was dubbed Gliese 1214. The diameter of this red dwarf turned out to be 5 times smaller than that of the Sun, with its mass just 15.7% that of the Sun. At the same time, Gliese 1214 is 300 times dimmer than our parent star, while its surface temperature is only 3000 Kelvin, or 2700 degrees Celsius. There is nothing particularly remarkable about the star itself. To be blunt, it is just another nondescript red dwarf that looks like any of the billions of other stars in our galaxy. However, in 2009, a solitary planet was detected in its environs, which was dubbed Gliese 1214b. With its diameter measuring 2.5 times that of the Earth, this exoplanet is just 6.5 times heavier than our home planet. Straightforward calculations show the freefall acceleration on the exoplanet's surface to be just 91% that of the Earth. The average density of Gliese 1214b is approximately 1,870 kilos per cubic meter. Judging by this comparatively small value, the exoplanet cannot realistically be made up of mostly metals and rocks, as is the case with our Earth, for example. But incidentally, this average density value seems to confirm the assumption that the astronomical body is 75% water or water ice and just 25% rocks. Thus, it appears safe to suggest that this exoplanet is an ocean planet. The object lies very close to its host star. The average distance between them measures just around 2 million kilometers, or 0.014 astronomical units, which is 75 times smaller than that between the Earth and the Sun. Also, the orbit eccentricity is rather high at 0.27, slightly more than that of Pluto. This means that in its perihelion, Gliese 1214b is approximately twice as close to its star than when in its aphelion. As for its orbital period, it takes the planet about 36 hours to complete it. The red dwarf Gliese 1214 may be 300 times dimmer than the Sun, but this incredible proximity to the star makes the climate on Gliese 1214b scorching hot. Supposing the reflection coefficient of the surface of Gliese 1214b is the same as that of Venus, the planet's surface temperature is supposed to be around 393 Kelvin or 120 degrees Celsius. If, on the other hand, the surface is darker, the temperature may reach as much as 553 Kelvin or 280 degrees Celsius. Due to the fact that the orbit of Gliese 1214b crosses the star's disk, scientists are able to carry out spectroscopic investigations of its atmosphere. Still, the results are rather ambiguous. If this space object really is an ocean planet, its atmosphere is supposed to predominantly consist of water vapor with some accompanying gases. Interestingly, no lines of hydrogen, helium, or complex substances like water, CO2, and ammonia have so far been detected in the planet's spectrum. It is thought that the outer layer of the dense atmosphere conceals its true content from the observer. The conditions on the surface of Gliese 1214b remind one of what it is like inside a giant steam boiler. Interestingly, the atmospheric pressure in its lower strata should be at least 15 times as high as that of the Earth. As the ocean and the atmosphere are in a state of thermodynamic equilibrium, the border between them is rather blurred. No wonder, as the density of water vapor just above the ocean's surface is practically equal to that of constantly boiling water. As we look deeper at the lower strata of the ocean, the pressure will continue to increase until we reach the depth of 100 kilometers. With the pressure value at this depth, water will be unable to remain in its liquid state even at temperatures this high. And so we will see the bottom made up of dense and heavy ice, whose thickness is estimated to be upwards of 5,000 kilometers. Thus, most water on the planet is concentrated here. Below the cryosphere, there should be the core, made up of rocks and metals. Unfortunately, chances of life evolving on any ocean planet are rather thin, even if the surface temperature happens to be more favorable than on this one. This is so due to the fact that oceans on planets like that are too poor in terms of microelements that are vital for living creatures. Even taking into account meteorites that occasionally bombard the surfaces of these celestial bodies, the chemical diversity is simply not good enough for life to originate here. Still, studying ocean planets poses a great scientific interest. According to NASA's mathematical modeling estimates published in 2020, there may be billions of planets of this type in our galaxy, both cold, harboring an ocean under an ice shell, and warm, like Gliese 1214b. Water is one of the most widespread complex chemical compounds in the universe, and this means that the chances of discovering new ocean planets are quite optimistic. Assumptions about the existence of space objects the size of a planet, which are independent from any star, have been around for a long time. Such celestial objects, freely drifting around interstellar space, are referred to as orphan, free-floating or rogue planets. Astronomical bodies of this kind emit very little thermal and light energy into space around them. It is suggested that there are no bodies in their close proximity they could clearly interact with or be bound to. That is why it is hardly surprising that these objects are so difficult to detect. The first potential representatives of this class of planets were spotted as recently as in the early 21st century. The warmest rogue planets can be detected with infrared telescopes, and others thanks to something called the gravitational microlensing effect. As one would expect, this class of celestial objects is one of the most mysterious and understudied. Today, only 3 astronomical bodies can be classified as rogue planets with a sufficient degree of certainty, with the overall number of rogue planet candidates over 24. Incidentally, according to the analysis of data collected in the course of the Ogle project, the Milky Way may supposedly be home to up to 100 billion objects of this class. This may only mean that right now we're at the very beginning of an upcoming series of discoveries in this field. Our notions of what rogue planets are like have long been based purely on assumptions and hypotheses. With the technological advancement of highly sensitive observation equipment, there arose opportunities to put them to the test in practice. The rogue planet lying closest to the Earth among those already confirmed is known as WISE 0855-0714. 7.27 light-years away from the Sun, it was detected in 2014 with the WISE Orbital Infrared Telescope. The astronomical body cannot be seen through optical telescopes, as it emits no visible light to speak of. The reason for this is its extremely low temperature. From 225 to 260 Kelvin, or 48 to 13 degrees Celsius below zero. In terms of its parameters, it resembles a cooled-off gas giant, and its age cannot be under 1 billion years. The rogue planet is mostly made up of hydrogen. However, in 2016, the Gemini Observatory produced evidence of the presence of large amounts of water in its atmosphere. It is suggested that water is condensed into clouds made up of tiniest particles of ice. Today, it hasn't been established for certain how this object came to be. There are currently 2 versions suggested by researchers. According to the first one, a celestial object like that starts its life cycle in the protoplanetary disk of a regular planetary system. Mathematical modeling of this process shows that if the original cloud of gas and dust is heavy enough, it is highly likely that at least one planet will be ejected beyond the system. The celestial object may also be forced out of its star's environs if another massive star passes it by, or else if its planetary system collides with another system. The chances of events like that are admittedly comparatively small. The other version has it that the space object was born just like any other star on compression of interstellar gas. At the same time, the mass of the object proved to be too small to unleash any thermonuclear reactions in its interior. It goes without saying that in this manner, it may turn out only as a gas giant or a brown dwarf, but not a rocky planet similar to the Earth. Some researchers don't agree that these objects should be seen as rogue planets and classify them as sub-brown dwarfs instead. Others suggest using the term planemo for all interstellar wanderers that don't show any thermonuclear activity. Bearing in mind today's notions of the makeup of brown dwarfs and gas giants, we may estimate the mass of WISE 0855-0714 at anything from 3 to 10 Jupiter masses. This rather falls short of starting a thermonuclear reaction, but quite enough to keep the heat effectively trapped inside the planet. Taking into account our knowledge about natural laws, we can predict what the conditions on the astronomical body's surface are like. For example, according to research by David John Stevenson from the University of California in the US, gas giants similar to Jupiter don't cool off instantly after receding from their star. Their thick hydrogen atmosphere is quite reliable thermal isolation, while the dense and hot nucleus made up of metallic hydrogen can keep the planet heated for a considerable time. Estimates show that the temperature of the lowest strata of a hypothetical celestial object's atmosphere may be high enough for liquid water to be around. It is likely to be present in the atmosphere as giant clouds made up of tiniest droplets. These deductions agree with the results of mathematical modeling of WISE 0855-0714 carried out by a team of scientists from the University of Edinburgh. It showed that the most likely temperature value of the planet's surface is 250 Kelvin or 23 degrees Celsius below zero. The celestial body's atmosphere also has a comparatively warm layer around 100 kilometers thick, whose density fluctuates from 0.4 to 1.2 milligrams per cubic centimeter. It is comparable with the conditions on the Earth, and so it is thought that this environment should be favorable for potential organic life. Incidentally, a planet doesn't have to be a massive gas giant to avoid freezing in the cosmos. In 2020, a rogue planet candidate was detected using gravitational microlensing techniques. And here is the long designation it got. It is still awaiting confirmation of the rogue planet's status, and its parameters have been defined only generally so far. According to preliminary data, however, the object is comparable to the Earth in terms of its mass and is anything from 30 to 180,000 light-years away. According to our current scientific notions, an object with a mass like that is not supposed to be a gas giant, and is more likely to be a rocky planet. This, in its turn, offers good grounds to believe that the object formed in the protoplanetary disk of a planetary system as the latter was forming. It may have been ejected from the system as a result of a cataclysm in space, or alternatively, under the influence of a larger neighbor. After that, it was left to its own devices and so became a free-floating planet. What will happen to it next is predefined by a combination of several factors. Provided the object's atmosphere is sufficiently dense, it will be reliably thermally isolated. Potentially, a layer of ice on its surface could produce the same isolating effect. In addition, with the object's interior scorching hot and with radioactive elements undergoing decay, most of the hypothetical ocean will remain in a liquid state. If the planet happened to have a moon, it may have retained it on ejection. If this is the case, tidal forces are likely to continue to deform and warm up the lithosphere. Theoretically, with any luck, primitive anaerobic life forms may have stayed around, although of course it would be next to impossible to discover their traces now. Most of the data about the rogue planets we know today were arrived at following mathematical modeling and complex calculations. It was possible to do these calculations thanks to the tiniest bits of information gleaned with the help of orbital and Earth-based telescopes. Even as I speak, a project is being worked on known as Cleopatra. Its main objective will be to search for free-floating planets and other objects in space with subsequent definition of their parameters. The project relies on something called microlensing. It is a phenomenon when a celestial body passes between a remote star and the observer on the Earth and briefly interferes with the light emitted by the remote star in the background. When observed from different angles, the moment of transition will be registered a fraction of a second sooner in one observatory than in another. Referred to as lensing parallax, this effect allows scientists to gauge the distance to a detected object as well as its mass and dimensions. An interplanetary spacecraft is planned to be created within the project. It is supposed to blast off the surface of the Earth as soon as in 2025 alongside a mission to Mars, after which it will enter its own orbit around the Sun. The project will be aided by a specialized artificial intelligence component, whose mission will be to process and analyze collected information. The Cleopatra project will certainly delight us with a wealth of exciting and important information, so there is a lot to look forward to. What is to become of all those rogue worlds out there, drifting quite by themselves in the dark depths of the universe? In theory, an orphan planet may be captured by the gravitational field of a star and become part of its planetary system, but this chance is by all accounts minuscule. Most objects like that are destined to wander for billions of years through endless expanses of space while slowly and inevitably cooling off. Eventually, they're to be swallowed up by black holes or else destroyed as a result of a cataclysm in space, never to reveal their secrets to mankind. There are quite a few really scary places in our universe. Most of them are cold worlds with no chances of life ever evolving there. But even among all this gloomy diversity, some objects can be singled out that may rightfully be called the most dangerous exoplanets ever discovered by now. And today, I invite you to check out the most incredible ones. Shortly before Halloween in 2020, NASA compiled a list of the most terrifying worlds. Among others, they included 6 exoplanets. Each of these objects' environments is not just extremely harsh for any living organism, even finding oneself in their comparatively close proximity may prove to be fatal. The first object on the list is a black gas giant, designation TRES-2b. This celestial object orbits the star TRES-2, which is a yellow dwarf lying as far as 718 light-years away from us. Let's take a closer look at it. Due to some unique properties of the chemical composition of the surface of TRES-2b, the planet absorbs over 99% of all the light shed on it. The nature of these properties remains a mystery, and chances are there are some chemical reactions taking place on the surface that we have never registered on any similar object before. And it is these properties that make TRES-2b the darkest exoplanet on the astronomical map of today. This gas giant was discovered on the 21st of August 2006, with more details on its characteristics obtained several years later. The mass of TRES-2b is 1.2 Jupiter masses, and its radius measures 1.27 times that of Jupiter. The atmosphere is as scorching as 1000 degrees Celsius, which gives the exoplanet a faint red glow like that of embers. Still, in spite of its gloomy looks, TRES-2b doesn't really qualify to be called the most dangerous place in the universe. There are many more objects lurking in space that are more terrifying than that. Let's see some more inhospitable ones. Here is another exoplanet, designation 55 Cancri E. It lies in the system of a Sun-like star, designation 55 Cancri A. This celestial object was discovered on the 30th of August 2004 by the Doppler spectroscopy method. Let's look at it in more detail. The planet's mass equals approximately 8 Earth masses, and its radius measures 1.875 that of the Earth. 55 Cancri E is tidally locked, and so it is always daytime on one side and nighttime on the other. That is why the side facing the host star is always heated up to a temperature reaching 2400 degrees Celsius, with the temperature on the night side 1300 degrees Celsius. These values are so high because the distance between the planet and its parent star is just 0.0183 astronomical units. Besides, volcanism on 55 Cancri E, which is thought likely to be there, causes dust clouds emissions. These clouds trap heat and effectively prevent it from escaping into space. The planet's orbital period is slightly under 18 hours. As for the atmospherical makeup, there is helium and hydrogen registered in it. There are also large amounts of carbon. Incidentally, this element is likely to form thick layers of graphite and diamonds in the planet's interior. 55 Cancri E isn't the only object in the planetary system of its host star. There are 4 other celestial objects orbiting it. The environments on these are by far more hospitable, which is the feature by which the 55 Cancri A system differs from the following object. It is dubbed Poltergeist, or PSR 1257+12c. This is an exoplanet lying in a pulsar system. The celestial object is located just 0.36 astronomical units from the system's center. This shows that Poltergeist wouldn't have survived a supernova that must have taken place before the pulsar had been formed. Consequently, the exoplanet is likely to have formed after this tremendous event, with the material for it coming from the nebula left after the explosion. According to another hypothesis, the pulsar may have formed after the merging of 2 white dwarfs. Unlike with a supernova, this process isn't always accompanied by a powerful blast. Still, as this is the first object of its kind we have discovered, science cannot give a definite answer as to its origins. The system with the celestial object lies 2,300 light-years from the Earth. Its mass is approximately 4 times that of our planet. As for its orbital period, it is around 66 days. Incidentally, the outstandingly powerful radiation emitted by the pulsar is enough to crumple any spaceship wanting to approach the mysterious exoplanet in its system. Even with all these properties taken into account, Poltergeist does not really qualify as the most dangerous exoplanet known to us. On approaching it, an astronomical body may simply get destroyed, but it would get positively vaporized in close proximity to the following object. The reason for this effect is the extremely high temperature on Kepler 70b, which is the hottest exoplanet known to us. The object orbits the subdwarf star Kepler 70. With a surface temperature higher than that on our Sun, it reaches 6,800 degrees Celsius. The object's mass equals 0.44 Earth masses, and its radius measures 0.76 that of the Earth. The celestial object's orbital period is 345 minutes. In other words, a day here is less than 6 hours long. Interestingly, the exoplanet regularly passes another object in the system, Kepler 70c, at a distance of 240,000 kilometers. To date, this is the closest that planets in space have been registered to pass each other. The extremely high temperature on Kepler-70b could be accounted for by the fact that this object may once have been part of its parent star. As for giving it the status of an exoplanet, it will take more evidence to confirm that it deserves to be given it, so this remains an open question. It should be mentioned that Kepler-70b is not the only celestial object we know of that interacts with its parent star so closely. Another object in similar conditions is the exoplanet known as WASP-12b. This celestial body lies 870 light-years away from our system. Its radius measures 1.93 times that of Jupiter, and its mass equals 1.46 Jupiter masses. WASP-12b is just 0.03 astronomical units away from its parent star. Due to this close proximity, the exoplanet has a temperature reaching as much as 2,200 degrees Celsius. The host star's extremely powerful gravitation slowly absorbs WASP-12b. Eventually, in approximately 10 million years' time, the exoplanet is expected to be destroyed completely. Bearing all this in mind, we will probably never delve any deeper into the nature of this exoplanet. It would appear that studying worlds of this kind cannot be high on scientists' list of priorities. However, some of these objects may happen to have some really unique features. Seemingly quite plain and ordinary, worlds like that may conceal many more dangers than would appear at first glance. When flying past the celestial body HD 189733b, for example, one might complacently think it a safe planet, as it resembles our Earth by its looks. But if one were to get as low as the level of its atmosphere, one would be exposed to some life-threatening dangers. For a start, the object's winds carry particles of silicate and develop velocities of 8,700 kilometers per hour. Besides, the rains on this planet cause precipitations of molten glass. The reasons for such hazardous weather conditions are extremely high temperatures and the atmosphere's peculiar chemical composition. Speaking about the exoplanet's orbital period, it is approximately 2.5 days. And it is highly likely that the object is tidally locked to its parent star. As usual, a quick overview of its main characteristics. HD 189733b is a bright blue gas giant orbiting an orange dwarf in the constellation Vulpecula. It lies just 63 light-years away from our system. The object's diameter is 1.1 times that of Jupiter, and as for its mass, it is 113% that of Jupiter. Interestingly, the distance between HD 189733b and its star is 30 times less than the distance between the Earth and the Sun and equals approximately 5 million kilometers. Due to its close proximity to the parent star, it has a constant surface temperature of as high as around 930 degrees Celsius on the day side, with the temperature on the night side never dropping below 425 degrees Celsius. Immediately on being discovered, the celestial body became a subject of investigations. In 2007, thanks to data obtained by the Hubble telescope, scientists found out that HD 189733b has a foggy atmosphere. Interestingly, when the planet transits between the observer on the Earth and its star, its atmosphere assumes a reddish hue. This effect could possibly be caused by the haze in the atmosphere. According to preliminary estimates, it consists of particles of iron, silicates, and aluminium oxide. Apart from that, the information beamed back by the Hubble telescope helped scientists establish that the planet's atmosphere contains water vapor, neutral oxygen, and an organic methane compound. Additional investigations revealed the presence of carbon monoxide on the day side of the planet. What prompted most questions, however, was the results of investigations revealing traces of methane of an unusual variety in the planet's atmosphere. This chemical element was shown to be in a peculiar fluorescent state when it emits electromagnetic radiation in the infrared range. This state of the substance is indicative of some unknown activity in the atmosphere of the exoplanet, which still remains to be found out. This is quite a clear-cut example of a situation when investigating an object like an exoplanet with an exceptionally harsh environment may yield unexpected results about some processes taking place there that will be a valuable contribution to science. And as the process of studying these worlds continues, they will remain no other than horror planets to us, as well as a solid reminder that we're more than just lucky to be the dwellers of our Earth. Earlier, in one of our previous videos, we have already taken a look at some terrifying and lethally dangerous worlds discovered in the vast expanses of space. With some of them extremely hot, others are located close to insanely powerful sources of radiation, and yet other ones are peculiar for some bizarre features on their surfaces. However, we haven't quite exhausted our list of the most horrifying planets, and now it's time to see some more. Our first stop is 202 light-years away from the Earth, destination K2-141, an orange dwarf. Its mass is roughly 0.7 that of the Sun, and its radius measures 68% that of our host star. With these parameters almost perfectly proportional, the star's temperature reaches 4,600 Kelvin, which is about 20% less than that of the Sun. And now to the planet in question. Just 0.007 astronomical units away from its star, there lies a really bizarre world, designation K2-141b. This rocky exoplanet is 5 times as massive as the Earth, with its radius 1.5 times as big as that of our Earth. All this gives us grounds to assume that the gravity on the planet's surface is at least twice as strong as that on our planet. The heavy metallic core, meanwhile, accounts for 20 to 50% of the planet's overall mass. It takes the celestial body about 6.5 hours to complete a full orbit around its parent star. Being extremely close, it is tidally locked to it. That is, it faces the star with one and the same side at all times. Observations show that the temperature on the planet's day side reaches 3,270 Kelvin or 3,000 degrees Celsius. This is enough not only to melt most rocks and metals, but also to effectively evaporate them. The day side of the planet is assumed to be covered with a lava ocean that never ceases to boil. The atmosphere is thought to be rather exotic, made up of steams of heavy metals and silicates. By contrast, the planet's night side is incredibly freezing. According to estimates, the temperature of most of its area is tens of times lower than that on the day side, and on balance, its values are supposed to be sub-zero. Mathematical modeling shows that this sharp temperature contrast gives rise to exceptionally strong winds whose speed reaches 1.75 kilometers per second. This is roughly 5 times the speed of sound, which means that the surface of K2-141b is continuously shaken by exceptionally powerful, deafening rumbling. It is assumed that on reaching the night side, atmospheric streams condense and precipitate on its surface in the form of fiery rain. This forms lava rivers, and eventually this molten metal makes its way back into a magma ocean to evaporate again later on and to continue this incredible, fiery circulation. However, this infernal cycle affects only a relatively small part of the planet's night side. The thing is that masses of evaporated elements from the day side simply don't make it to the main part of the night side and precipitate somewhere on the border. That is why the central part of the night side is likely to be a freezing desert bound with layers of solid rocks. Remarkably, K2-141b is far from being the hottest planet that we know of. For example, there is an object referred to as Kelt 9b lying 670 light-years away from the Earth. Its surface is as hot as 4,600 Kelvin, which is approximately 4,330 degrees Celsius. Just to compare, The outer layers of almost all red dwarfs, for example, are much cooler, which means that in terms of temperature, this exoplanet is quite a match to stars. Its parent star, designation Kelt 9, is of a whitish-blue color and has a mass 2.6 times that of the Sun. As for its diameter, it is 2.3 times that of our star. The surface temperature of Kelt 9 is rather high at approximately 10,170 Kelvin, or a staggering 9,900 degrees Celsius. This largely accounts for the extreme conditions on Kelt 9b, which lies quite close by. Just 0.035 astronomical units away from its parent star, the planet completes a full orbit around its system's center roughly every 1.5 days. Kelt 9b is a hot gas giant. Compared to Jupiter, its mass is 2.8 times as big, and its radius measures roughly twice as much as that of the largest planet in our system. Based on today's notions about the composition of this type of planets, the inner part of Kelt 9b's atmosphere is supposed to be even hotter. Estimates allow for this value to reach as much as 11,000 Kelvin on account of heavy metal ionization. With this figure so exceptionally big, it appears that the planet's atmosphere should contain vaporized iron and titanium, alongside the elements we're used to in an atmosphere's composition, such as hydrogen or helium. Its close proximity to the parent star and the extremely high temperature cause the planet to gradually lose its atmosphere. By and by, powerful stellar wind blows it off into space, which is why the object is shrouded in a cloud of rarefied gas. This material will eventually be attracted and absorbed by the star. Interestingly, according to some estimates, the exoplanet loses up to 68 Earth masses every billion years. Theoretically, in a long while, Kelt 9b may well get stripped of all of its atmosphere and transform itself into a Chthonian planet. However, its parent star is likely to hit the final stage of its life cycle long before that, swallowing up and destroying all the celestial objects within its reach. The space objects we have just looked at are a living proof, as it were, of the fact that stars can destroy the planets close to them and not just warm them up. But incidentally, there are celestial objects out there in the universe that have experienced their parent star's wrath in full measure. One of such objects lies 4,570 light-years away from the Earth in the environs of a small star, designation V391 Pegasi. Now, the star is a white dwarf whose mass is twice as little as that of the Sun and whose radius is approximately 23% that of our parent star. The temperature of this celestial object is unbelievably high, at almost 30,000 Kelvin. All thermonuclear reactions in its interior would have run their course a long while ago. Up ahead are hundreds of billions of years of slow cooling, with the white dwarf eventually transforming into a black one. The planet we will look at, referred to as V391 Pegasi b, is in this ordinary star's environs. Its lot is exceptionally amazing. According to mathematical modeling, the planet not only survived its progenitor star shedding its outer layers, but actually found itself almost within the star for some time. It is assumed that when the system's star V391 Pegasi transformed into a red giant, its outer layers, extremely rarefied by then, were almost brushing the planet's orbit. Their density became dozens of times lower than the atmospheric air we're used to, which means that the celestial objects devoured by the dying star remained whole for a while and didn't get destroyed at once. It goes without saying that they would have been losing their speed and dropped into the star's hotter and denser layers. Still, V391 Pegasi shed its outer layers sooner than V391 Pegasi b melted and ceased to exist as a whole object. At the moment, the exoplanet appears to be a gas giant, 3 times as massive as Jupiter. Its orbit passes 1.7 astronomical units away from its parent star, and it takes the planet approximately 1,170 Earth days to complete a full orbit around its system's center. It is still not entirely clear how this astronomical body managed to preserve such a big mass after its collision with the scorching hot layers of the star. Their influence was supposed to have destroyed the object's atmosphere completely. However, there is no doubt that the host star's collapse brought about some dramatic changes, both in terms of the exoplanet's orbit and its parameters. That is why it is hardly possible for us to ever find out what V391 Pegasi b was like before immersing in a sea of raging plasma. Space expanses conceal uncountable astronomical objects with the most bizarre properties. Some of them are almost totally invisible through regular telescopes, but can be detected by looking at radio wavelengths when exploring space. An example of such like celestial objects is pulsars, neutron stars spinning on their axes at a mind-boggling speed. These object spectra are peculiar for exceptionally fast and regular pulsations. That is why it is quite easy to detect another celestial body transiting between a radiation source like that and an observer on the Earth. This is precisely the way our next object of interest was discovered. But first we'll be looking at a pulsar which lies around 4,000 light-years away from the Earth. This neutron star boasts quite a long name. Here it is on the screen. And now let's check out its remarkable features. The pulsar's diameter is just a measly 20 kilometers, and its mass is approximately 1.4 that of the Sun. The object spins at an incredible rate, with roughly 10,000 rotations a minute, while continuously emitting powerful electromagnetic radiation impulses. Now the surface of the exoplanet, our next object of interest, is continuously exposed to these waves of lethal radiation, which makes it a hostile and forbidding place. It takes this planet just 2 hours to complete a full orbit around its system's center, and the distance to the pulsar is smaller than the Sun's radius, just 600,000 kilometers or 0.004 astronomical units. Incidentally, the celestial body's surface is bound by eternal cold in space as its parent star just barely emits thermal energy. The object's mass is around 330 that of the Earth, while its radius is 4 times that of our planet. This makes gravity on its surface as much as 20 times stronger than on the Earth. Estimates show the planet's average density to be about 23 grams per cubic centimeter, which is more than most chemical compounds we know. The planet is thought to be made up for the most part of crystallized carbon under a lot of pressure. Besides, the object's upper layers contain some oxygen, which is probably chemically bound with carbon. It is highly doubtful that a celestial body located so close to a star could possibly have survived a supernova event. It is more realistic to assume that the exoplanet formed after the progenitor star had come to the end of its life cycle and had transformed itself into a pulsar. The exoplanet could be a piece of debris left over from a white dwarf whose material would have dispersed for the most part. This makes classifying the exoplanet an especially difficult task. Still, whatever it is, this world remains one of the most dangerous and hostile ones lurking in the depths of the cosmos. Amazingly, even having covered thousands of light-years, we have made acquaintance of only a minuscule portion of the endless diversity of our galaxy's exoplanets. Hundreds of billions of other worlds still remain concealed from observation. However, every day we find out more about the universe. And what seemed unlikely yesterday may become quite feasible even tomorrow, which may only mean that there are a great many discoveries yet for us to enjoy up ahead.